Hey everyone, today I'm going to show you guys red-black tree insertions, just giving you guys a quick overview of red-black trees. And this is kind of just focused for DSA students and people who just want a quick overview or grasp of red-black trees. So first, a red-black tree is a binary search tree that stays balanced using color rules. That's it. So before I go over the actual insertion and color rules, let's explain why staying balanced is so important. So on the right is a simple, normal binary search tree, and as you can see, it's in the worst case, so it gets kind of tall, and it's similar to a linked list. So if you want to do an insert or search or remove, you'd have to traverse through every node, which would be O of n time complexity. On the other hand, the red-black tree, it adds a Boolean flag, in this case is red, and following the red-black tree rules, it allows the red-black tree to have a search, insert, and delete time complexity of O log of n, which is guaranteed. And the use cases are std map in C++. There's also more functions in C++, functions in Python, and also Java, routing tables, and caches. So now let's go over the actual rules for red-black trees. And if it violates any of the rules at all, it is not a valid red-black tree. So first, a node is either red or black. 2, the root is always black. 3, a red node always has black children. An easier way to see this is no consecutive red nodes. So 4, the number of black nodes in any path from the root to a leaf is always equal. 5, null nodes are always attached to all leaves, and null nodes are equivalent to black nodes. So I'll put the rules in the top right so you guys can refer to them whenever we do the examples, but now let's go over the insertion. When you insert as a red node, and whenever you run into a problem where you invalidate the rules in the top right, you fix it by either rotating or flipping the colors in the tree. So for the first example, we're going to insert to an empty tree. So for 2, you insert it as a red node, and as you can see for rule number 2, the root is always black, so you just flip the color. The next easy case is when you have a black parent, and so it violates no rule if you insert a red node, and so as also rule number 3 says, no consecutive red nodes, so if you can see the tree, it makes sense that it won't violate. But problems arise when you have a red parent. So there's 2 different cases, and we have to focus on the uncle. So circled on the right is the uncle, which is just the sibling of the parent, or whatever is on the same level as the parent of the node you're inserting. And if there's nothing there, remember that null nodes are black nodes. So that's the uncle. So for the subcases, we have if an uncle is red, we flip the subtree colors. If an uncle is black, we rotate. And these are similar to the rules, the after rotation and after flipping colors. This is what you should color them in. And so if you have a cheat sheet or you're able to memorize these, this is very helpful, and I'll put them in the bottom right as well. So here, if you can see the node we're inserting, we're violating rule number 3. So we look at if uncle is red, we flip subtree colors. And by subtree, I mean the actual subtree of not the one you're inserting. So you take this, and then you flip the subtree colors. Just flip. And then so now, this tree is almost fully correct, but remember, the root is always black, so the root is black. And again, this tree is valid, and the reason that this is valid is because it violates some of the rules, but also it may seem like it does, but because of you're just changing the first root. But remember, rule number 4 says the number of black nodes in any path from the root to a leaf is always equal. So it goes 1, 2 to the left and 1, 2 to the right, and the rest is fine. So now I'm just gonna remind you guys this is a binary search tree, so there is gonna be numbers. So now let's say we're inserting 3 again, and in this case the uncle is null, so the uncle is black. So if we look at the cases, if the uncle is black, we rotate. So we have to, it is a left-left rotation case here. If you haven't gone over rotations, I recommend going over that before looking at red-black trees because it's just part of the actual use cases. So you have to rotate at 6 here. So we just do a right rotation at 6. So as you can see, we rotate over, and I'll go back so you can kind of visualize it. We're just moving it to the right, and now it's balanced. But as you can see, circled again is after rotation, we have to color it because as you can see, it is also invalid here because there's 2 red nodes, and it also invalidates rule number 5. So we just color it like that, bam, and the tree is now valid. And so thank you guys for watching. This is just a quick overview. There's much more convoluted cases, but for a quick grasp of the ideas, this is everything you need.